In this video, we're going to train a multi-layer perceptron neural network to emulate the Lorenz dynamics in an autoregressive fashion. For this, we will first go over some theory, then we're going to create a dataset out of 9 trajectories and analyze their corresponding Lorenz maps. This dataset can then be sliced into windows to train our network with making one-step prediction into the future. We will do a very classical deep learning training setup running for around 5 to 10 minutes on a laptop CPU. We will assess its convergence and then produce trajectories of the emulator against the trajectories of the Runge-Kutta simulator, and we will see that they are quite close to each other. And also when it comes to the Lorenz map, the emulator does a fairly okay job, and we'll discuss that in further detail. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video and the last one in the series on emulating the Lorenz dynamics, where we will now finally emulate the Lorenz dynamics. Just to recall, the Lorenz system was a system of 3 nonlinear ordinary differential equations in terms of 3 state variables, x, y, and z, which we conveniently collected into a 3-dimensional state vector. Then we were interested in its temporal behavior, so we created a trajectory, so in other words, a sequence of snapshots, and we did so by recursively applying a simulator to it. Let this be denoted by calligraphic P, and we started at an initial condition and then eventually get a trajectory which then revealed the butterfly shape. For this video, we are now interested in approximating this simulator, so the calligraphic P, with a neural network, and we do so by tuning its parameters so that it's denoted here by an underscore theta. And since we have a mapping from a 3-dimensional vector space to another 3-dimensional vector space, so we will also mimic the signature of the simulator, the most reasonable architecture to use here is a multi-layer perceptron. Just for completeness, I've again listed the Lorenz equations here as these 3 nonlinear ordinary differential equations, and the Lorenz equations are a prototypical example of so-called deterministic chaos, in that they expose or that they have a very strong sensitivity to the initial condition, but also show these very intricate patterns in their state space, so in other words, the butterfly shape that we saw in the previous videos. We defined the simulator, so the calligraphic P, in terms of an explicit Runge-Kutta force scheme. So this is an ODE integrator with 4 stages, which we rigorously implemented in one of the previous videos. But now we are approaching it more loosely in that we now just say, okay, let us train a network based on data to do essentially the same as the Runge-Kutta simulator does. And so we will create data trajectories from the Runge-Kutta simulator and then have the network predict one step into the future, both across the trajectories and across time. We will do a little bit of a mini batching across both samples and across time. And then the network essentially, or hopefully, will try to imitate the numerical simulator, and we will see how good it is at doing so by evaluating it on the Lorenz map, which was this scatter plot of 2 subsequent maxima or local maxima in a z coordinate. We will again have the same settings as in the previous videos, which also matches the settings in the original paper by Lorenz. Well, then let's get started and go down. So the majority of the notebook I have here is still from the last videos, so we will just go over this to repeat this. And then after we've done, we will continue with the MLP emulation. You can use one of the timestamps in order to jump there directly if you prefer. Okay, let's get started. So we first need to introduce some additional imports. So we will have JAX, of course, JAX NumPy as well, and matplotlib.pyplot, but we will also need the JAX tree utilities. So import jax.treeutil as JTU. Then we will import Equinox as EQX. So Equinox is a deep learning framework in JAX that provides us with tools for doing deep learning training and also with architectures. And in our case, we will just use their multi-layer perceptron architecture. Then I will import Optex, which is a gradient processing library, which provides us with the Adam optimizer. And then ultimately, I will import the TQDM progress meter to monitor our training. So let's shift enter that. And then let's go through the subsequent cells. So this was in the first video. I will also have it linked up here, where we implemented first the Lorenz right-hand side, and then we implemented the Runge-Kutta 4 method in terms of an autoregressive simulator. So here you also again see these 4 stages of it. We were able to instantiate it, and we also used some default parameters, which are exactly the ones that come from the Lorenz paper. And then for start, we chose an initial condition consisting of just ones, so where we only had one initial condition essentially. And then if we applied the Runge-Kutta simulator to it, it produced another 3-dimensional vector. So it mapped from the 1, 1, 1 state to another state essentially. And this behavior of taking a 3-dimensional vector and producing another 3-dimensional vector is essentially what we then also want to have with our multi-layer perceptron. Then we had some legacy version of creating the trajectory, which we used in the initial NumPy implementation, but it turns out that it is more efficient with JAX, especially for these autoregressive rollouts, to use JAX-like scan, which is a lower primitive in JAX. I also have a video linked up here on more details on this primitive, but essentially what it allowed us is to perform a function transformation taking an autoregressive stepper, so one which has a signature mapping from 3 to 3-dimensional vectors, into something which maps from a 3-dimensional initial condition to an entire trajectory, even including the initial condition. This is what we did, and then essentially we had a trajectory with 5001 snapshots, so one snapshot for the initial condition and 5000 subsequent steps. Ultimately, this gave the butterfly shape that you might be familiar with or might have seen before. Then in order to assess whether what we did is correct, we judged it by the Lorenz map, which is a scatter plot of the 2 subsequent local maxima in Z direction. So this is a snapshot or a screenshot I took from the original Lorenz paper. So we analyzed the signal in Z, where we had the initial transient phase, and then essentially we are now interested in relating these peaks here. For this, we wrote a function that extracted these peaks, and were then able to do this scatter plot and saw that it matched the Lorenz paper, so we had a good conclusion that this was a reasonable trajectory. And then in the last video, also linked up here, we implemented parallel or vectorized simulation by translating the code to JAX. For this, we are now interested in simulating or producing trajectories for multiple states at the same time. And for this, we started by drawing a set of initial conditions, so not 9 initial conditions at a time. And then we were able to use the JAX.vmap transformation, which allows an stepper or a function to operate on an axis with an additional, on an array with an additional batch axis. And then there were essentially 2 ways to nest both rollout and vmap transformation. We chose for the version where we have vmap over rollout, and this gives us an array of batch, time, and state. So where we have the 9 batch dimensions, we have the 5001 time dimensions, and then the 3 state dimensions. We plotted all the 9 butterfly shapes at the same time and saw that qualitatively they're quite similar, but of course the ultimate trajectory produced can greatly differ. Then we extracted these Lorenz maps for all the trajectories and plotted them, and thereby also saw that all of them are valid Lorenz trajectories. And with this, we come to the point where we now implement the autoregressive MLP emulation, and we already have kind of a data set with these 9 trajectories, but I want to redo the data set such that we now have 5,000 time snapshots which are within the chaotic attractor. Because if you recall, the first time snapshots are this transient phase where we will start at an initial condition and we move towards the attractor, but technically we're not on it yet. So let me write this down. So we will redo the data generation, but this time discard the first, oh, my copilot still seems to be on. Never mind, it's the one markdown cell I wanted to do for this video, so let's keep it on. So, and then we will discard the first 2000 time steps, and we will do so and call this as a burn-in or as a warm-up phase. Very nice, copilot. Okay. Whatever, let's go to the next cell and do exactly that. And let's call this a data set now. And again, we will use the vmap over rollout transformation. So jax.vmap over rollout applied to the Lorenz stepper with now 5,000 plus 2,000, because we do this 2,000 warm-up step. And we will also not include the initial condition this time. And then apply this to U0 set, so keeping the initial conditions of before. If we executed that now, or let's just do it, and then look at its shape, we will see that it now has 7,000 entries. But let's discard the first 2,000 steps already. So let's have the indexing here with colon and then 2,000 upward. And now this gives us 5,003, which is essentially 9 trajectories within the chaotic attractor. Then we can split this dataset into a train dataset and a test dataset. Let me scroll down a bit, which is taking the dataset, and for simplicity, we will just use 6 trajectories for training and 3 for testing. So let's take the first 6 for training and then take the last 3 for testing. So now we have these train trajectories, and if we go all the way up to where we looked at the problem formulation, I wrote down that the learning task over the parameter space of the MLP will be a so-called one-step supervised training, meaning the network makes one-step prediction into the future, and technically the simulator as well, but here we will just simplify it in that we just use the data that is already on the trajectory, so the simulator is never called on the fly, although of course this would also be possible here. So what we have to do is, in order to simplify the mini-badging later on, we will slice all trajectories, all of the 6 training trajectories, into windows of length 2, because we need, for a one-step supervised setup, we need both an initial condition and a reference, or like a future state, or if you think of in terms in classical supervised deep learning, we need an input and a target. So this is what we're going to do now. Let me go all the way down here. And for this, I want to implement a function which operates on one trajectory. And then again, we will make usage of the vmap transformation to have it operate on an entire set of trajectories. So on the entire set of 6 training trajectories. So let's call this function define slice windows of 2. And this one takes one trajectory, so I just wanted to make this here very verbose. And then essentially, how does that work? So we will iterate over all possible windows within the trajectory. So if we now have a trajectory which is of length 5,000, it has 4,999 windows of 2 in there. So in order to know how many windows there are, I first want to extract how many times snapshots there are. I mean, we know it's 5,000, but I just want to keep this more general here. So number of time steps is essentially the one trajectory dot shape indexed at 0. And now we have to be careful. So this function is designed to operate on an array without a leading batch dimension. So indexing the shape at 0 will give the number of time steps. Later on, when we do the VMap transformation, JAX will cleverly rewrite the function for us such that this still is correctly deduced from the array. Then let's create a list of windows and then iterate and say for I in range of num time steps -1. So here this was 5,000. This now is 4,999. We will append to the windows a window extracted from the one trajectory. So let's use one trajectory and then index it from I to I plus 2. Sorry, to I plus 2. And of course we need to do +2 because the upper index in a slicing is not inclusive. So meaning that, for instance, if I was 5, that would be from 5 to 7, but this would only include the 5th and the 6th entry. And of course, thereby we get a window of size 2. And then eventually we can return the stacked version of the windows. So we will use jnp.stack on the windows, because here we have a list of arrays, and this then stacks it together in order to get an array which has another leading axis. Okay, let's do it exactly that. And then we can get train sub-trajectories as a representation for these windows by using jax.vmap on the slice windows of 2 applied to the train dataset. And if we now take a look at its shape, we see it is 6, 4,999, 2, 3. So it again has 3 state dimensions. Then we have 2, let's say, window dimensions. And then we have 4,099 of these different windows. And we have 6 trajectories in total. And ultimately, when we then do the mini batching, we want to mini batch over both this axis and over this axis, because we want to sample across the trajectories and the cross time. I mean, technically with these chaotic problems, or like we have here with the Lorenz equation, these axes seem to be very similar, because if you ran the Lorenz integration for long enough, you would eventually like fill this chaotic attractor manifold. But here we see that the 6 trajectories do still look different enough such that it's worth sampling across all of them. And in order to do so, we will merge the batch axes by concatenating them together. So we will use jnp.concatenate on that, and this will merge these 2 batch axes. Let's execute that. And if we now take a look at it, we see this one is now 29,994 to 3. So again, 3 state dimensions, then the window length of 2, and we have 2,994 windows across all trajectories and across time. That does now conclude our dataset, and we could technically now start our training loop, but we would be missing a data loader. So I just want to copy in a very simple data loader. Let me copy that over and leave that here. So this is going to be a generator which we can use in a loop, which takes a data set and the batch size and the shuffling key and then yields batches until it runs out of it. Then we can continue with the actual training loop. So in this cell, I first want to start by instantiating our neural architecture. And let's call this the Lorenz Emulator. So no longer the Lorenz stepper. And as said, we're going to use the multi-layer perceptron architecture from Equinox. So we will have eqx.neuralnetwork.mlp, .mlp. And then for the MLP, we define the in size. So we have a 3-dimensional input. The out size is also 3-dimensional. The width I want to set to 160. So we have 160 hidden dimensions or hidden neurons in the hidden layers. And the depth I want to set to 8. The activation should be the ReLU. So we can get the ReLU by jax.neuralnetwork.relu. And then we need to provide a key for pseudo-random reproducibility. And this will be jax.random PR and G key, and for the simplicity, we will use 42. Why not? Okay, so this is our Lorenz emulator. Then we need to instantiate an optimizer for the problem. So let's do optimizer. And I want to use the simple Adam optimizer, but not with a constant learning rate, but with a learning rate schedule. And Optex also comes with many popular learning rate schedulers. And here we're going to use the warm-up cosine decay schedule. And this essentially works as if we have a first phase in which our learning rate rises linearly, and then afterwards there is a so-called cosine decay, which means that we have the learning rate drop in form of like the half period of a cosine, and this will allow us to reduce the learning rate to a very low value, even to a value which is 0, which we're also going to use. And so we force the network into convergence towards the end. I experienced this learning rate scheduler to be quite advantageous for these autoregressive neural emulation problems, because the problem with autoregressive neural emulation is that we train the networks on doing one-step prediction into the future, but ultimately we want them to be used as the simulator, which could work multiple time steps autoregressively. So they will only learn to do one step in the future, but then later on we will have them do 5,000 steps autoregressively. And I have the impression that when we have the learning rate fade out to 0, this is advantageous in order to force them into a convergence which stabilizes their long-term behavior. Let's add some values to this learning rate scheduler. So we will start at 0.0. So initially the learning rate will be at 0. Then we're going to peak at 3e minus 4, so 3 times 10 to the minus 4. And we will do 15,000 update steps during the warm-up, and then the total schedule will be 100,000 steps. So out of 100,000 steps, the first 15,000 are the warm-up, and then the latter 85,000 steps are the cosine decay. So this is now recorded in terms of update steps. We will soon roughly translate this into mini batches and epochs. But with the optimizer instantiated, we can instantiate its state by saying optimizer.init and then apply it on the representation of the parameters it's supposed to optimize. And we will get them out of our Lorenz emulator by using a filtering routine from Equinox. eqx.filter on the Lorenz emulator with the filtering rule equinox.isArray. If this sounds a bit strange to you, I will have a video linked up here with more details on the training loop or the deep learning training loop in Equinox, which you can take a look at if this was a bit too quick what we implement here. Okay, then next up we can implement the loss function, which is our one-step prediction into the future. So this one takes a model, which will then end up being the Lorenz emulator, and it would also take a batch. And so this will be a mini batch of data. And now taking a look at it, so the train trajectories have this shape of the batch dimension in the beginning and then 2 free. When we then do the mini batching, we will slice smaller parts out of this axis. So for instance, let's say we use a mini batch of 64, then the shape of the array, which is gonna be represented by batch, is 64 to 3. And then out of this array, we can extract a collection or a batch of initial states and target states. That's for deep learning terminology, let's just call them X and Y. And they are batch indexed at :0 and batch indexed at :1. So we take all the samples in the mini batch and then use the 0th point in time, so the first snapshot in the window, and then the first point in time, the snapshot thereafter in this window. And therefore we created these windows of size of 2. Then we can create a Y prediction by using the model on X. But here we have to be careful. In Equinox, all models are single batch by design, so they only operate on arrays with the predefined size. So in our case, if we have an in size of 3, They only operate on arrays with one axis having 3 dimensions. But now, after we extracted the input, it will have 2 axes. The latter axis will be the 3-dimensional state axis, and the beginning will be the batch axis. But again, we can make usage of the JAX.remap transformation to make this work correctly. Sorry, this did not work, but let's add the brackets here. And then ultimately, we can reduce the prediction and the reference into a loss using a mean squared error. So doing jnp.mean over jnp.square of y prediction minus y. Then once we have the loss function, we can implement an update function, which is essentially the heart of our optimization, which performs both the forward pass, the backward pass, and the parameter updates. This one takes a model, a state, and batch. And by state, I mean a representation of the optimizer state. Then the first step is to do the forward and backward pass. It will obtain both an estimate of the loss and the gradient. And thereby we have to apply the autodiff engine of JAX, which is conveniently wrapped within Equinox to correctly work with their architectures by saying equinox.filter value and cred. Sorry, value and cred, and then apply it to the loss function, and then apply it to the model and the batch. Then we can use the optimizer to update the state of the optimizer and to get an array of updates to the network parameters. So it's called as updates, and new state is optimizer.update on gradient, state, and model. And then lastly, we can use the updates to apply them to our model to get a new model or a model with updated parameters, which is going to be equinox.apply updates to the model with the updates. And then ultimately this function will return the new model, the new state, and the loss estimate. And since this is the greatest computational effort in our training loop, we will place a just-in-time compilation around it, but we also need to use one of the filtered routines in in Equinox to have that work correctly. So you'll do @equinox.filterJIT. And then with the update function, we can finally do our looping. So let's start by instantiating a shuffle key. This is going to be used to also have the pseudo-random mini badging being reproducible. So we will say jax.random.brng key, and let's use 99 for this. And then let's also instantiate an empty list in which we can record the train history or the train loss history, such that we can then later on visualize it. And then we will have 2 loops. So we have an outer loop, which is the loop over the epochs. So how many times we're going to repeat our data set. And then an inner loop, which is related to how many mini batches we have in one epoch. So let's start with the outer one for epoch in a range of 200. I will explain soon why we will need 200. And I want to wrap this in a TQDM statement such that we get our progress meter. And then within each epoch, we are going to split the shuffle key into a key responsible for this particular epoch to then call our data loader. So we will override the shuffle key and create a subkey with jax.random.split applied to the shuffle key. And then with the subkey, we can instantiate our data loader and say for, or maybe scroll down a bit, for batch in data loader applied to the train subtrajectories. Let me have that load and set the batch size to be 64. I will also explain that in a second. And then use the key subkey. And as that, this will be this generator which provides as many batches until it runs out of batches. And then essentially we will call Lorenz Emulator, opt state, loss, and call the update function on the Lorenz emulator together with the opt state and then the current batch. So essentially what it does is calling this update function, and then when it returns the new model, or in particular the model with the new parameter, it would override its current state of that, and it will also override the optimizer state. And then we can attach or append the loss to the train loss history. So train loss history dot append loss for the visualization later. Okay, then I decided to do 200 epochs with batch size of 64. Why is that the case? So first of all, 64 in my experiment seemed to be a reasonable batch size. If we do 64 and then make some back of the envelope calculations, so let's go up here. So we have 2,994 samples of window length of 2. So this means if we divided them, so let me do a little bit of the math here. So 2,994 divided by 64 gives us 469 mini batches per epoch. So essentially this inner loop will have 469 elements. And then let's have this round. So this is around 500 elements, so 500 mini batches per epoch. And if we now do 200 epochs, we will in total do around 100,000 update steps. And this is approximately matching these 100,000 we set in the learning rate scheduling, because the learning rate will converge to exactly 0 after 100,000 steps. So if we did more update steps than the 100,000, beyond that, they would all be associated with a learning rate of 0, which of course would not give us any update. But so now we are doing less than that. Let's also crunch the numbers here. 469 multiplied with 200 means that we will do around 94,000 update steps. So this should be well below our 100,000. It also means that our learning rate schedule does not correctly end at 93,800, which is a little bit rough. Of course, we could adjust that here, but I just want to have this being round numbers here. Okay, anyway, let's execute that cell such that we get our training started. So it will now take a little bit for making the compilation, just-in-time compilation work, and then we should soon see that we have at least 1% of progress. Okay, here we go. So now this took a little bit forever to make the first epoch, but that's of course because my recording software is running in the background. I will skip to the point where we have completed the training, and then we will continue from there. Okay, great. Here we go. The training has finished. Let's display the train loss history, and let's use a plt.semilog.y on the train loss history to get that. And here we go, hopefully. That took a bit longer than expected. So we see on the x-axis the update step that we're in, and then on the y-axis the training loss that we got. So we have this very strong fall down in the beginning, and then we have a very noisy phase, but we still see some progress happening. And then towards the end, this cosine decay is kicking in. As mentioned, we will not fully converge to 0. So if we did, I guess the spread would get a bit smaller as well. But still, this allows us to get rid of this very strong noisy period here, and then end up with a state towards the end, which hopefully is usable. And ultimately, we decreased the loss by 1, 2, 3, 4, 5, 6, 7-ish orders of magnitude. So that should be a good start. And let's see how the network is actually operating. In order to assess its performance, we will need the network to produce a trajectory. So I already mentioned that we trained the network on doing one-step prediction into the future, and now we will roll it out. So we'll now have the network feed on its own output, and this will be challenging for it, and let's see how it performs with that. So let's call this the emulator trajectory. And for this, we will again use a vmap over rollout. So we will do jax.vmap over rollout applied to the Lorenz emulator. And then we will do the rollout with 4,999 steps and set include init to true. So why do I do that? Because we will have the networks kick off their trajectory with the 0th snapshot in the test trajectories. So we will do the test dataset here and index all the samples and then index the next axis at 0 such that we get the initial state in there. And if we, for instance, did 5000 and set include init to false, the trajectories of these two would be shifted a bit. So the reference trajectory of test dataset would include this initial condition, but wouldn't have these 5000 and first step, you might say. And by doing exactly that, we get 4999 snapshots which are actually unrolled, but we will also have this shared initial state which the emulator trajectory and the test dataset share, have them both at the 0th position. Okay, let's kick that off. Then I want to copy in some plotting code, which essentially does a similar plotting as we had before with the 3-dimensional trajectories. But now we will do a subplot with only 3 plots in there to plot the 3 test trajectories that we have. And then we essentially do 2 trajectories within them. We do the corresponding true trajectory, or the one that is given by the Lorenz simulator, given by the Runge-Kutta force scheme, and another one with the emulator trajectory given by the MLP. And I also included this up until snapshot, so meaning that we first don't plot the entire trajectory, but only the beginning, because then we might be able to spot how quickly those two will diverge. So let's execute that. And here we go. Now we have 3 different trajectories. It's very hard to say where they start because they do lie both very closely on top of each other, which I would say is a good sign, such that the MLP does something reasonable and comparable to the Runge-Kutta simulator. So let's see how that looks like if we change the up until to 200, so that we plot not just 20 steps, but 200 steps. And here we go. So by now we should be able to see where both trajectories started. So for instance, in the left example, they likely started both here and then they followed each other quite closely. But eventually the orange emulated trajectory will start to diverge from the true trajectory. And this is to some extent also expected because we have these chaotic problems very sensitive to the initial condition. It is very unlikely that we will fully reproduce the Runge-Kutta simulator, so it's very unlikely that we get the exactly same behavior. But still, even with these expected deviation, it's still surprising to see that the trajectories align that well with each other. I think that's already quite a good start for our training. Let's also plot the entire trajectory of the 5000 steps. So we will just set the up until to -1 to include all snapshots. And now we should get a qualitative perspective of how well the emulator can produce a butterfly shape. And I would say it's doing a fairly decent job at that. So we see that it fills, or like it seems to fill out the manifold similarly to the true trajectory, but also there is an interesting other observation that the emulator seems to be stable. So over the 5000 steps that we rolled it out, it didn't diverge. So we do see that it stayed on this same manifold, or at least approximately stayed on this chaotic attractor manifold. And I think this is an interesting achievement because if you look at it, again, we only trained it to do 1 step into the future prediction. And now it fed on its own output 5000 times and it still hasn't diverged or not went away from this chaotic attractor, which I think is a good achievement. As a last step, let's also evaluate the Lorenz maps to see how well the emulator matches those in comparison to the simulator. So let's call this the maximal values set true, where we again have to use the list comprehension because JAX VMap does not work, inconsistent shapes. If you want more detail, this was in the second to last video where we implemented the Lorenz map. But let's do the list comprehension and say find maxima and set applied to trajectory for trajectory in test dataset. And then we have the maximal values set emulated with find maxima and set applied to trajectory or trajectory in emulator trajectory. Let's kick that off. And then I will also copy paste a plotting code to show these three Lorenz map side by side. So here we have the Lorenz map corresponding to the trajectory that we have up here. And in blue, we see the Runge-Kutta simulator, where the points really follow these like two hyperbolic arcs, you might say, that are very typical for the Lorenz map. Just to give you a reference, I will show you again the screenshot I took from the paper of Lorenz, essentially those here, these two arcs, and that the points also did not scatter away from these two arcs too much. I mean, in his version, there are some which do not lie on this line directly, but this scattering away is not that strong. And let's go down to the comparison again. And here we see that, again, the blue trajectories or the blue scatter dots do follow that, which is expected because we already saw that earlier, that the Runge-Kutta simulator is doing a fairly decent job at that. But then in orange, we have the emulator, and we do see that there are some significant deviations. So I would say that this is really noticeable, and probably if you had some slightly worse training setup, you might see these deviations even stronger. But still, I think even with these deviations, that's still a good result, I would say. And probably with some more tuning, one might be able to more closely match this particular shape. But I will leave that up to you. So the notebook can be downloaded from the video description. Feel free to play around with it. Feel free to add some additional performance boosts, how we can make the MLP emulator become as good as the Runge-Kutta simulator, for instance, by increasing the training dataset or making some augmentations to architecture or the optimization setup. Feel free to share your results in the comment sections. There's probably some very interesting things one can do here. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. If you enjoyed this video, then please leave a like and consider subscribing to the channel. There's way more content on neural emulation of ODE and PD integration. Here you will now find similar videos, and I hope to see you in one of the future videos.